Hello, this is Dr. Christy Patton-Lukes, and we're going to be talking a little bit more about reactive processes and choosing those hypothetical process paths, and then we'll continue by looking at fuels. So the key to computations with reactions is to select a hypothetical process path that includes the standard heat of reaction. So if I have materials coming in at Tn and Pn, and they come out at T out and P out, whether this be a closed or a steady state system or some variation of that. The key thing is that no matter what these temperatures and pressures are, I want the reaction to take place at 25 degrees C in 1 atmosphere. So I'm going to take the feed and bring it to 25 degrees C in 1 atmosphere and have a path that does this. So it might be constant temperature and pressure. Okay, so it may be 2 steps, but the path is going to first bring the reactants to the standard temperature. Then we'll have the reaction occur. And this is going to still be at 25 degrees C in 1 atmosphere. But now I have products. I may have some leftover reactants as well, and then I'm going to take a step where I have my products and I will return those to the final temperature and pressure. And again, I may need to do this in a constant temperature and a constant pressure stage. So this outline here shows 5 possible states. I may need more than this if I have changes in phase, okay? But the key thing is that I need to include this piece here at 25 degrees C in 1 atmosphere that is the reaction. So let's look at an example. This is a bit of a more complex example than what we've looked at, and I have other videos that I've made reference to in the Canvas website. So in this example, ethylene oxides form from ethylene by the reaction C2H4 gas plus 1/2 oxygen gas forms C2H4O gas. Now let's suppose that I have 3 moles of C2H4 with 2 moles of oxygen fed to an adiabatic reactor at 400 degrees C 1 atmosphere. In this particular case, the conversion of the C2H4 is 25%, and what we want to know is what is the temperature of the product stream. So recall that adiabatic means that Q is equal to 0. And the way this problem is described, we have no kinetic or potential energy changes. We have no work being done. We're told that Q is equal to 0. So I know that I'm going to be working with an energy balance that basically says for steady state reactors, delta H plus kinetic energy change plus potential energy change is Q plus W. But in this case, I'm left with just delta H is equal to 0 because all other terms of my energy balance are going to be 0. So I'm going to be looking at a change of enthalpy from the inlet to the exit. And I've got the material coming in at 400 degrees C 1 atmosphere. So I can 400 degrees C, I'm going to take it to 25 degrees C. This is going to be my feed material. And then I'm going to let the reaction happen. I'll still have some of the raw material feed, but I will go to a final state of temperature, still all of this at 1 atmosphere pressure. So these will be my products. So my calculations in this case will require 3 stages of calculations. So I need to do a material balance as well as an energy balance in this case. My system is pretty simple. I have a feed that's 3 moles of C2H4 with 2 moles of O2, and I'm going to have coming out some C2H4, the rest of it because the conversion is only 25%, the rest of the oxygen, and some of the product C2H4O. So I can write a material table on this. I can use things such as the definition of conversion. Let's do those calculations. So to do the material balance table, if my feed is stream 1, my reactor, and my product is stream 2, then my material balance is going to include C2H4, O2, and C2H4O. If I look at this all in terms of moles, then I have 3 moles of C2H4, 2 moles of O2, and 0 moles of C2H4O that are fed. So a total of 5 moles. I also find that it's very helpful when I'm going to be doing combined mass and energy balances to go ahead and list the temperature and the pressure. So it's at 1 atmosphere and it's at 400 degrees C. Okay, now what's going to come out, I don't really know. I'll identify these as A, B, and C. I know that there's a change in number of moles. I have 1.5 moles in on the reaction, only 1 coming out, so I don't really know what's going to come out. I just know that it's the sum of A, B, and C, and all of these things will be in moles. I also do not know the temperature, but I know that there's nothing that's changing the pressure, so the pressure we'll assume is also 1 atmospheres. So now let's look at the conversion. Okay, in this case, the conversion is 25%. 3 moles of C2H4 come in, and A moles come out. Divide that by 3. This is the definition of conversion. Therefore, A is 2.25 moles of C2H4. Okay, so how much C2H4 reacts? 3 minus 2.25 says that 0.75 moles of C2H4 react. This tells me that 0.75 moles of C2H4O will form. Okay, this is going to be C. And tells me that half of 0.75 which is 0.375 moles of O2 will react. And so therefore B, 2 moles of O2 come in, 0.375 react, so therefore 1.625 moles of O2 will leave the system. So A, 2.25, B, 1.625, C, 0.75, and the total is going to be 4.625 moles coming out. So next I need to do the energy balance. So from this particular case, my path is going to be 3 moles of C2H4 plus 2 moles of O2 at 400 degrees C that I'm then going to bring to 25 degrees C. Okay, I'm going to calculate that energy using delta H, and I'll number this one 1. It's going to be the integral from 400 to 25, 3 times C sub P of C2H4 plus 2 times C sub P of O2 dt. Now the next piece of this is going to be the reaction. So after the reaction, I'm going to have 2.25 moles C2H4, 1.625 moles of O2 plus 0.75 moles of C2H4O at 25 degrees C. In this case, delta H2 is going to be 0.75 moles react times delta H for the reaction. And then I have my final step where I'm going to have all of this stuff. At the final temperature. In this case, delta H3 is going to be the integral from 25 to the final temperature of 2.25 times C sub P for C2H4 plus 1.625 times C sub P for O2 plus 0.75 times C sub P for C2H4O. Now C sub P for C2H4 and CP for O2 are both in the book. CP for the C2H4O, ethylene oxide, is given here in the problem statement. I can also calculate heat of reaction. Doing these, I found that this delta H1 is negative 92.6 kilojoules. I'm going to leave that to you as an exercise. And using the heat of reaction times 0.75 moles reacting, this is negative 77.5 kilojoules for delta H2. Now delta H3 is going to be a function of temperature, okay? And so it's going to be a function of the temperature. So what I'm going to do is I'm going to set up an equation, 92.6 plus negative 77.5 plus this function of temperature that comes from this integral here, okay? That is going to equal 0. So I went to Excel. If you wish, there's a plugin you can download, or you can just work with Excel as is. And the plugin is Apex. There's instructions in the book. But anyway, this is a spreadsheet add-in that can allow you to do this calculation a little bit more easily. But I just did this in Excel. I typed in the function f of t with these other things here, and I used solver to set this equation equal to 0 by changing T. And I put in a first guess of temperature equal to 25 degrees C. I had Excel just brute force change T, and the solution that it came up with was 912 degrees C.